Good afternoon, everyone.
Good afternoon.
We have 2 or 3 questions and doubts to clarify. The first one is, what's the reason to decide to use the multiplication or divide instead of minus or plus?
Okay.
This is the first question. And the second question is, it's not clear for us the state variables. I think there are 3 state variables. It's not clear to us which one. What are the 3 variables among the 6 the 6 variables discussed in the first session.
Okay.
And if possible, which variables is internal and which variables are external variables. Yes. I think this is the questions. We have three points. Thank you.
Okay, thank you very much. I'll start with the first one. In F1, that is the first relationship, we have a product of D, the shop density, multiplied by the population in the catchment. The shop density in the area of the market area where the inundations happen, and the population density is how much people there are in the entire catchment, 13 square kilometers. So why did we multiply them and not add them up? The reason is the following. The income of the shopkeepers, which is what F1 represents, the annual income of the shopkeepers is in the area is proportional to the density of the shops in the area. If there are double the shops in the area, the income in the area will double. If they triple the shops, the income in the area will triple. And similarly, the number of the clients the shop have is related in our equation, our model, to the total population in the area. If there are twice as many people, there will be twice as many clients, and there will be twice as many annual income for the shopkeeper. If you have triple the population, 3 times as much income. So let us assume 3 times as many shops, 3 times as much income per shop. So the result would be the product would be 3 times 3, not 3 plus 3. That's why we multiplied D with P. Do you understand my explanation?
He's not in the line anymore.
Okay. I hope you understand it. Okay, second question related to the state variables. State variables have 2 meanings. One is the physical meaning and the other is the mathematical meaning. In the physical meaning is state variables. Okay. In the physical meaning of state variables is different from a flux. Like, for example, discharge would be a flux. Temperature would be a state. So fluxes are never state variables in physics. In mathematics, this often is the same, but can be also slightly different because this really depends not so much on the physics, but on the way you write the model equation. A state variable embodies the entire history of the past. For example, the number of people in this room would be a state variable, and it replaces the entire history. So I'm not interested in how many people came in an hour ago or 2 hours ago and how many people left. It's only the result of the history. The entire history is projected to one point in time, to now, to represent the state. And this is usually also what physical state variables do, actually. So that's why the physical explanation is meaningful. Let us look at our list of variables, right? G, the money of the shopkeepers, is clearly a state variable. So how much money they have on their bank account or at home, under the bed maybe, that's a result of the past history of income and expenses. So it's clearly a state variable, both in the physical and the mathematical sense. The shop density also is a state variable, also physically and mathematically, because you build new shops, you remove shops, and the result at any point in time is how many shops you have now. And I ignore the history, how they came about. I'm only interested how many shops are there now, a state variable, mathematically and physically. Now, the mean annual flood discharge physically is a flux. Physically is not a state variable. But we, in the model, let us see how we use it. Q, that's F5. In the model, we don't treat it as a state variable because we just say it's proportional to the population. I would not consider that a state variable. It's just a flux. Q can happily be a flux in the model. Okay? Water level, that's 3. Also, so there's no balance equation, no change of the state variable with time. So Q is a flux, and water level is, I would not consider water level as a state variable because mathematically, because it is, we don't have a differential equation, it's just an algebraic equation. And physically, is water level a state variable? I guess it is, right? This is the result of the history. Cross-sectional area in the model is definitely a state variable because it results from the history of people have widening the channel and narrowing the channel and widening again. And the result of that is the state cross-sectional area. I would consider this a state variable, definitely in our model. Not sure about physics, whether area is a state variable. Not sure. Population is a state variable. Number of people increases and decreases, and the result is a state, physically and in the model. And also, where do we have P? Where's the equation? It's external. So now this was responding to your question, what is a state variable and what is not a state variable. You were also asking what is external and what is internal. We have one external variable, which is P, the population in the entire catchment. We are saying it has nothing to do with the dynamics on the marketplace. It has to do with the fertility of the population, with the economic situation, and other things which is external to our model area. So it's external. It's the only external variable which we have, which is very little. Usually we have more. For example, as hydrologists, we very often have precipitation as an external variable. We could do that actually very nicely. And then we can, it's very easy, we can put in precipitation with Q. It's very simple, and then we can look at climate change effects, for example, with the model. As hydrologists, we like to do that. Okay, no answer? No, probably not. Maybe he can type whether it's, yes. It was clear to him.
Professor Fredo? Did Professor Günter answer your question? Okay. Okay, thank you.
Very good.
That's
very
perfect.
clear.
Thank you.
Okay, thank you. Okay. Do you have any other questions? Shall we continue? We're not yet at the end. There's still things to do. These are not the final equations. This was our first shot at the equations. And when you build this model, you need to iterate and iterate a couple of times. There are a couple of things I would like to discuss with you. First, we need to think about the physical units, the dimensions, of the variables. First. Second, we should look at the behavior of these equations, particularly the limiting behavior. If we have variables that go from 0 to infinity, for example, like area, population, 0 to infinity, or 0 to 1 if you scale it, we need to look what does the equation give us if we put the variable to the minimum value and if we put it to the maximum value. Is the result meaningful? this analysis of the limiting behavior helps us with refining the equations. We don't need to put this into a computer program to understand the limiting behavior. We do this before. And then when we put it into the computer program, then the limiting behavior will be okay. It will be what we expect. If we don't do it now, you'll be really confused because, you know? Okay, dimensions, limiting behavior. And let's do that, at least for some of them, right? Just you see that how this works. Dimensions. And dimensions and the range, the definition space, right? The definition range, we call it space. It's defined from 0 to infinity, for example. Okay, let's start with the money. What? Why me? Why me? Okay, who is volunteering for? Let's start with the units, right? Who would like to do units? Yes, please. Units.
Yeah, okay. I'm going to need help, so. Sorry.
Please. So we are now talking about these 6 variables.
Okay.
What units do we give it? And then we need their definition space, which is related to the units, of course.
Okay, G is money of the shopkeepers. So we can give, I don't know, reais, maybe? Reais? Brazilian currency?
I can't understand you well.
Brazilian currency. So
okay,
G,
what's the, yes?
the unit of G is reais.
Very good. How do you pronounce it?
Reais. Reais.
Okay, I know why I asked you to present it. Very good reason for it.
I'll say.
Okay.
So and the interval is 0 to infinity, maybe? Yes.
You're not allowed to make debts. Yeah, good question, yes. If you say 0 to infinity, you are not allowed to make debts.
Okay,
Debts,
so
the
minus
debts.
infinity to infinity.
So if you have no
Maybe.
money, do you go broke out of business or do you make a debt? Take a loan?
Okay, yeah.
Well, we need to decide. It can't be either. If you have no loan and the model simulates 0, then end of game, right? So no loans or loans. No loans. No loans.
Minus infinity to plus infinity.
Will they get a loan from the bank? If I were a bank, I wouldn't give them a loan. What do they have? They have a shop, and next flood takes the shop away. What guarantee do I have to get my money back?
0 to infinity.
I mean,
Okay?
no, I'm a banker, so. But of course, you could also do minus, right? It really depends how you want to conceptualize it. Okay?
Okay. So
Shop density.
Shop density is
Oh, that-
H.
Yes, yes.
Yes.
So that's easy. It
It's
cannot
a-
be negative.
Shop per meter, square meter? Kilometer or meter?
Doesn't matter.
Doesn't
It's the same thing. The same thing. Shops per square kilometer. Okay, that's very good. And now with the range, you
is 0.
no
can-
negative shops.
No negative shop, so
This
0 to
now this is a very good question. Do you want infinity or do you want a maximum?
a maximum, I think, because it's square meter. So, but I don't know how much. 1
Well, you just call it max.
max.
You don't need a number now, right?
Okay.
We call it max. So we had the new parameter, the maximum number of shops.
Okay, and then
And this just a second.
okay.
This max must appear in the equations. You realize that. Without max in the equation, we will never get a max. You will get infinity. Okay? Good, very good.
Now it's mean annual flow discharge in the city center. So it's cubic meters per second. And the interval, maybe it's 0. We can have a negative. And max, maybe, or I don't know, max.
So limit discharge.
Yeah.
Who is the hydrologist among us? What about maximum discharge? Does it exist?
No.
We have a hard time, right, with the maximum discharge. But we could, for the model, we could say maximum discharge. Just take the limit very high. Then it doesn't make a difference if you want to, right? It's up to us.
From Vienna, they have a suggestion for the
Erase. G.
okay. They will speak on Skype.
No, on G, I think that could be a negative because they have employees sometimes. So if they lost their shop, they don't have a way to pay those people. So I think that could be negative because they will they will have debt not for the bank, but for employees, maybe for suppliers. Não sei como suppliers. So I think that could be minus infinitive to plus infinitive.
So
But just my opinion, I don't know.
minus infinity.
There's nothing wrong and right. I mean, there's all
To
the
plus
options. Okay, can we hear to the
Can be negative.
Francina?
Yeah, the same. Minus infinity. So that's okay. And the discharge is max, or we can plus infinity? The Q. Max? Okay.
Okay, so you say it can be negative in case of losses, the G. For example, if you have losses, it can be negative.
Well, G is the total money the shopkeepers own, not the annual income or loss. DG on TT is the annual income or loss. G is the total what they have. So they can have like 1 million and then they lose 100,000 per year, but they still have 900,000. So it's not inconsistent with having losses. But if it's negative, it's a loan. They need to take up a loan. They have less money than nothing, right? A debt, which we now introduced, right?
It's how much they are in the bank. Their bank account, maybe. But there's loans, so I don't know. Eles vão ver? It's G is not exactly. It's the bank account. They can have loans, so they are in debt with the bank, but their losses are not directly affect. They affect, but they have already in the bank something. I don't know if I'm clear.
Change what they have.
Yeah, the loss changed or what they have. I don't know. I can.
Okay,
Okay.
let's continue.
So the water level is meter, the unit, and W is 0 to max. I think it's not infinity, or the water level is max, I think. And cross-sectional area, square meter, 0, not exactly, it can be 0. 0 to max. And P, the population is 0. Population is habitant. To infinity or to max? Infinity? Infinity? Max? Max, okay.
Very good.
Okay.
We happy with that? There's still one ambiguity. We can.
From my point of view, population should be like a limit, a maximum value, because we know that small cities, like growing, developing cities, they follow like a linear growth, but like large cities, more old cities, they follow like a logic growth curve. Yes. Logistic curve.
Thank you. Would you like? Okay.
It's okay?
Very good. There's no one more thing, one ambiguity about the A cross-sectional area. What is it? What is A? Can somebody help me what A is? Is it the cross-sectional area of the river that, like, or is it the area that is wetted by the water? So is it the cross-section of the stream, or is it of the river bed without the stream? So when there's a flood, does A increase, or is it just what is available and does not change with the flood? Okay, do you understand my question? What is available? So is it the way we have it in Manning's equation
Yeah,
or
because
not?
here is the rectangle, no? The channel. Here we put that A is the rectangle because we define the ratio.
That what is wetted
Yeah.
here,
The
right?
wetted-
So this is something we should reconsider if we want the potential A and not the wetted A, right? That
But
we
it-
were confused. This is something
If-
we make a note. Maybe not need to change it now, but
If you change this, we put this into a coefficient.
yes.
So this is just Q over A, and this is a coefficient.
So the
And even A could be a coefficient to the power of, I don't know, alpha.
so maybe not make it not A, but B, the width of the channel. Then it's clear, right?
Okay.
If we replace A by the width of the channel, then we know it has nothing to do with how much water there is. It's just a variable that purely has to do with the geometry. And this is what we want, right? Okay.
Okay,
But
I
just
change.
make a note or, yeah.
A is like the length of the channel here. I can change B to B, or no? I don't know if you can.
I'm not sure. It would be, A would be W times B, probably. But just make a note.
Okay.
Need to replace A by B. It's hydraulics. We don't need to do the hydraulics now. Okay. Very good. Very good. Thank you very much. Thank you. Super.
No.
Well done. We need another volunteer, but now we have the limits, we have the units. We now need to check whether the equations have the limiting behavior what we want it to have. Okay? And you will be surprised that we need another volunteer. And now there are not many people who have not volunteered yet, so it's getting easier. Right? You're smiling, you've already been out there, but not everybody has. Please. Oh, yes, come outside. Yes, let's put the hand together. Very good. Now, what we have is not very difficult. So we maybe don't have to do it for all the equations, but let's start with one equation. Let's do this one, F1, right, for the money.
Right.
And we... Now, what is your name?
My name is Talita.
Salisa.
Talita.
Salisa. I'm learning a lot, but 3 days is not enough. Now what we need to do, we have the limits for the variables. And if we put the limits into the equations, we see what we get. We do this now, not in the computer program. Okay? So what variables do we have? We have W, we have D and P, right?
D and P.
Three
Okay.
variables. Let's, for example, let's make some space here on the right-hand side corner and start with the limit, the minimum values for all three of them. And then we take the maximum for all three of them and the minimum for one and the maximum for the other and see what we get. Okay?
Okay. So first you have W, and it's 0 to max. So how do I write here?
Well, you can just simply write F1 is minus beta times 0, which is the minimum,
Okay.
plus beta, which is different
get
beta.
it.
D is 0.
And P. Yeah.
Okay. Is 0, which is 0. Okay, is this a good result or a bad result? Is it what we want or not? What does the equation stand for? Is it what we want or not? The equations should do what we want, not the other way around. We and the master, they're the slaves. Okay, so let's see what water level is 0, meaning no flood. Okay, if no flood. If you have no flood, water level is 0. What is the next variable? The next variable is D. You have no flood and no shops in the area and no population in the catchment. The income of the shopkeeper does not change with time. Yeah. We agree with that, right? Okay. They have no fixed expenses, for example. You could think of having fixed expenses. They have to pay the rent for the shop. Then this would not be true. They have no income and would still have a loss, which in reality is actually the case. Okay, but then next. Next limiting, yes?
Yes, so the maximum.
Yes.
In W, we have max. Oh, yes. And
Max for max of what? What is of
for
the maximum water level?
Yes.
Make it W max maybe.
Okay.
Yes. W sub max. So maximum water level, the highest flood level that you can think of. Okay. Plus.
Wait a minute. And F1 and and the max for G, it's also max. And the max of B,
Okay. So if you have, well, first let's try the other case and the first term, 0, no flood. Yeah, let's put 0 here first. Remove it and replace it by 0. So just put 0 first here.
okay.
It's a more useful case to start with. So the case now is no flood, maximum density of the shops, and maximum density of population in the catchment area. Business is booming, isn't it? And then their money their shopkeepers have should go up very quickly. Does it do that? Very good.
It's great.
Okay, works. And then now let's do the flooding case.
Okay, so this is the max, and
let's
one
do,
of these
for
is
example,
zero?
yes, let's do all three max, maybe. So we have a full catchment of population is at maximum, shops are at maximum, and a big flood, the biggest possible flood. Maximum, probable maximum flood. Probable maximum flood, they call it.
So
Okay,
which
yes.
one is the zero?
Yes, also max, for example, yeah.
D max?
D max and P max, yes.
Okay.
Because if you said one of them is zero, nothing is happening. If there's no shops, no income. Okay, what's happening now? Is this positive or negative? If f is f1 bigger than 0 or smaller than 0?
It depends.
For this case, depends on the coefficients, of course. Should it be bigger than 0 or smaller than 0? Probably smaller than 0. If it's the largest flood that can occur, even if you have all the business in the world, there should be damage. So this should be smaller than 0. You can, on the left-hand side, you can write smaller than 0. This already helps us with setting the coefficients. You see? We have a lot of freedom, too much freedom to select the coefficients, but we have some constraints to get this result we want. Very good. Would you like to have another equation, maybe? Is the one
another? I don't know. Another one of this?
The F4 maybe. Is the F4 is interesting?
This.
F4 is interesting, yes. The bottom left, is there some space?
Where?
Bottom left. Yes,
Now.
here. No. Here's some space.
Okay.
If we should consider the water level after it extrapolate the limits of the channel, because we just have economical losses after it reach the when it comes out of the channel. Because we are considering.
Okay, you're saying we should not have economic losses for W being very small, then only beyond the threshold. Correct?
Yes. The zero should be
The bank full water level only when it goes beyond the bank full water level. Correct? Yeah. Okay.
It could be a condition to the variable.
To the, maybe not the variable, but to the equation. Can you change the equation maybe with a different color, with blue?
Okay.
Change the equation in a way that the doubt is accounted for, yes?
We were saying that maybe we could consider the water level only above the limit of the channel. But in that case, the F3 equation would be wrong, because this equation is for channels, channels,
Yes.
and it's above the channel. So the equation for the water level is not right.
So what
Well,
we do now?
It's not correct anyway, because we need to account for area, for the total area, right? So we know there's something that needs to be fixed. Yeah, but what we can do, we can say W minus W bank full, only if it's bigger than 0. Which, when you solve differential equations, is not nice, because it produces a nonlinearity, and then it messes your numerics up. So preferably no thresholds, if you can avoid it. Power laws are much better than thresholds. But let's now write it down. What equation is it that we need to change? This one, the F1, isn't it?
Yes.
This one, yes? So we need to write, sorry, you need to write W minus WB for bank full, right? This would account for what you've been saying, correct? And this term should be bigger than 0. If it's negative, we don't have a gain. They don't make money if the water level is below the bank, right? Should be greater than equal 0. It's W minus WB exactly, and the entire thing greater equal 0. So if it's negative, we don't count it negative. We don't make a profit if the water level is below the bank, right? It's just if it damages, it goes above. You agree with that? I think this was a very good idea. Okay, should we make another limit? No, we're finished, right?
Yes.
We're finished, or one more?
No.
No.
That's great.
Okay, I think, thank you very much. You understand the... It's called a hot potato.
I don't understand. What?
Please come outside. So you understand the system, right? Of course, you do this for all of these things, and then you fix the equations. If you find something that's inconsistent, now we are not very careful. We actually should fix the equations, because sometimes things are inconsistent. We did one thing, but probably there are more things to fix. But if in a smaller group, usually you do this 2 or 3 persons together, you're much more efficient, of course. But maybe you don't think of everything. If bigger group has a broader outlook, it's less efficient, but is more robust, because we can think of more things. Okay. What do we do next?
I don't understand the step 7.
Okay. But we're now at 5.
Yes.
And let's do 6 first? Or do we want to talk about 7?
About 7.
Okay. Fair enough. We wait. We give it another 10 minutes and you do 7. Or would you do 7 now?
No, I don't understand what I need to do in step 7.
Yes, I understand. Yes? And my question to you is, should we do step 6 now? And would you like to do step 6? Or would you just prefer to wait, and after 5 comes 6? So we do 6 now.
I can do 6 now.
You do 6 now,
Yes.
and then of course you can ask questions for 7. Of course.
Okay.
Okay. Can you bring up? Can you bring up our table for step 6? Which is good. You understand step 6. You can explain it to us. Very good. Parameter estimation. Can you tell us a little bit about parameter estimation?
Actually, I can't. How can I infer from response? I don't know.
No. What are the parameters here in our model? What would you consider a parameter, a model parameter?
The G, key, the variables.
No.
No?
No? What are the parameters in the betas? The betas are these things. These are the model parameters.
Oh, the
Have you
constants.
ever calibrated a model?
No.
No, okay.
No.
So have you ever looked at a model? Like you have not used the model? Not so much.
I don't have any experience with models.
Nothing to do with model?
Yes.
Okay. I think we let you sit down now, and then you help us with step 7.
Okay.
Okay. Thank you very much. Anybody would like to talk about model calibration, parameter estimation. Has anybody calibrated a model in this room? You have already been, you have calibrated a model. Please come outside. I think, okay, you tell us about something about parameter calibration, how you estimate model parameters. We're now talking about, we have the equations, but we have, how many coefficients do we have? 8? I'm afraid we have something like 14. What do you think? Okay, let's count together. Right. Can you just count them and we just check? 1, 2.
1, 2, 3, 4, 5, 6, 7, 8. 9, 10.
15.
11, 12, yes, 15.
15 parameters. 15 parameters. Okay, what is the idea of a parameter? A parameter says the model is universal, conceptually, and the parameters are adjusted, the coefficients, for the local situation. We have 5,500 communities that are like São Carlos. The parameters we estimate here are for São Carlos. The model could apply to 5,500 communities around across Brazil. That's the idea of the model, right? Parameters are local, the model structure is universal. And then we estimate, how can we get parameters? How do we get parameters?
Using empirical data.
Yes? Please elaborate.
If you have observed data here, we put into the equations, then we do regression analysis.
Okay.
So we get the parameters.
Okay. So what data would you observe for F1?
We have water level, D, and P.
Yes. So why don't you underline what we observe?
Yeah, for F1, we have water level, population, and shop density. Right? Here, here, and here.
You observe all three things.
Yeah, I think it's easy to get this. Right?
Sure. You're doing the study, I'm just observing. So we observe WDP. And how do you get beta W and beta D if you have these three? I don't understand how you get this beta if you observe three variables.
Yeah.
You also need F1.
Yeah, we also need the GDT.
The G and the D. Okay, then also the circle.
Yes.
So we observe dg on dt and W and D and P, and from that we estimate beta 1 and beta 2, conceptually. But in reality it doesn't work, because you usually don't have water level at the same time as D and P, right? So conceptually it's exactly what you're saying. In practice, not so much. So in practice we calibrate parameters of models. Have you calibrated a model?
Never.
Never? Hey, what have you been telling me? What have you been doing? What did you do?
On here, you mean?
With models.
With models, just using.
Using the models. And how did you get the parameters of the model?
Usually, for my master's, I just get the model calibrated.
From somebody else? Who did it? Somebody in the room?
No.
How did he or she do it? Secret.
I don't remember.
Okay.
I don't know how to explain the process.
Okay. Thank you very much.
Gabriela calibrated high mode.
Okay, we will ask her. Okay, thank you very much. So, Gabriela, you calibrated high mode.
Yes.
How did you do that?
Well, I manually, I put some. First, I look at the parameters and I saw what they mean.
What
the
they mean.
parameters mean.
Yes, we have done that.
Yes, we have done that. Then I look up to my area and see what should the parameters do in the model. So I just how can I say I just guess some values. I guess some values
Assume
and
some
run the
values,
model,
yes.
and I see how the model behavior.
Yes.
And then I just guess another one, and I do a calibration by Pareto. I don't know
Yes.
how to say that in English.
That's Pareto, yes.
Yes. And that's basically what I did.
But nobody in the room knows what Pareto is. I can assure you.
Yes, for sure.
We can also talk about Pareto. But the more fundamental thing, I'll try, thank you very much. I try to explain in the most fundamental way. So what can we remove here? Maybe we can remove this here. Is this okay? Limiting behavior. So when you have a model, you have an input and you have an output. And you have okay, we can discuss Pareto later. We can discuss what Pareto is later. At the most fundamental level, with a model, and it's not just socio-hydrological, it's for quantum physics, for anything a model, right? You have an input, you have a model structure, which are the equations. These equations, the multiplication and the D and P is the model structure. And then you have model parameters, which is our beta and the W max, these are parameters. And then we have an output, which are the variables. So it would be, the input would be, in this case, P, the population, and or maybe also precipitation, if we want to include that. And the output would be the G, the D, Q, etc. You throw P, the population, evolution of population in the past 50 years at the model, and you give the model the betas and the max into the system, and then you press the button, the model simulates, and then it produces a time trace of G. So the input looks like this. It's a time trace, function of time, P. Population grows, goes up. And then the model simulates G and simulates D, the density, and maybe the G goes up, but it may go down, and it may where's Q? Okay. And density may go up and may go down again. This is the output of the output of the model. The G and D is the output. And also the other variables, A and W. And now, the trick is, you have observations of that. You observe that. And you have observations of that. So you have simulations, GDQ, the blue things are simulations. GDQ are observations. You observe how much money the people have. You observe the number of shops. You simulate the money. You simulate the number of shops. You simulate the discharge. And then you vary the parameters. These parameters, you vary them, bigger, smaller, in a way that the output of the model matches the observations. So this G should be equal to this observed G, the density should be equal to the observed density, the discharge should be equal to the discharge to the observed discharge. So you have an input, then the model simulates, and then you fine-tune the coefficients. You make it bigger or smaller, right? And then you make it bigger, then it goes, the output goes up, you make it smaller, like when you have a stove, yeah, for cooking stove. Make it smaller, heat goes down. You switch it on, goes up. And then you just turn the handles in a way that the output that the model simulates is as similar as possible to the observations of the same variable. You understand? If an input, coefficients you to tune, then if an output, go up, down, until it matches ideally exactly the observed variables. That's called calibration. Okay? And this is also what you did with your model. You did exactly that. Okay, that's called calibration or parameter estimation. Not just in socio-hydrological models, in all models. Ideally, these coefficients we could get it from somewhere else, right? From the literature or from measurements. If you can measure the coefficients, the beta, it's much better. Some coefficients you can measure, for example, the gravity in a model that has Newton's law has gravity, and you measure gravity, right? It's even better. Often we cannot measure the coefficients. In most cases, we cannot. If you build a model where you can measure the coefficients, you're saying, what do they mean? It's much better, but it's not easy. So in most instances, they cannot be measured. We just change them around so that the output of the model, the simulated output, matches the observation. Okay? Good. How do you do that? If you have one coefficient, it's very easy. You just turn it to the right, then output goes up until it matches. Bingo. Calibrating one parameter is very easy because you only have a limited number of combinations. About this estimation, generally in socio-hydrological models, but also generally in any kinds of models. The more parameters you have, model parameters or coefficients, yeah, same thing. The more parameters you have, the more difficult is it to estimate the model parameters. So let us assume the model parameters have 100 useful values. The parameters can go from 0 to 100, and I want to decide which one is the best. Is 12 or 74, right? So I run the model 100 times, and then I take the best. Very simple. I only need to run it 100 times, then I look at the 100 outputs, compare them with the observation, and take those that are closest. The distance between the simulation of the variable and the observation of the variable is called objective function. It's usually the difference, sum of the squared differences is a typical objective function. You look at the difference, observed G, simulated G, delta, the difference, square, and for all time steps you sum it up. Sum of squared differences. And if it's 0, you have a perfect match, which you never have, of course. We minimize this function. So, and if we have 100 possibilities for one parameter, we have to run the model 100 times. Not a big deal. Okay. Now, if you have two variables, alpha and beta, I need to vary alpha 100 times and beta 100 times in all combinations. So I need to run it how many times? 100 times 100 times the model, which is 10,000. And I do all combinations, and then I pick the best objective function. No problem. I can run the model 10,000 times. No problem, right? You know what the story, how it continues the story, okay? You can guess it. So if I have 15 variables, how often do we have to run the model? 10 to the 30 times. Right? One variable 10 to the 2, two variables 10 to the 4, 15 variables 10 to the 13 times. Right? And if it takes a second to run the model, it takes the age of the universe to do all the simulations. Right? We cannot do it. That's why we need clever methods of parameter estimation. You did this manually, probably. Yes, because you're very clever. Only 6 parameters, but that's still 10 to the power of 12. You did not 10 to the power of 12 simulations, only few of them, and you select them in a clever way. If you understand how the model works, you can do it manually well. The disadvantage of that is when you submit the paper, the reviewers will say, how did you choose the parameters? And then you're saying, well, I had an inspiration. That's why I selected parameter 1 as 17.3. And then your reviewers will say, I have a different inspiration. I will reject the paper because I don't know how you selected the parameters. So in practice for engineers, this is a very good method. Reviewers don't like it so much because it's not repeatable, because they don't know your intuition, which may be very good, your intuition. So for publications, usually people use an automatic calibration. Automatic calibration is exactly what I said, try all of the things out, but in a cleverer way. So you don't need 10 to the 30s, these model runs, but fewer. And there are algorithms to do that. So in principle, there are hundreds of different algorithms. And if I think some of you heard systems theory or systems analysis. Who was that? Yeah, some of you. It's about optimization. And they will talk about linear programming and gradient methods. And you have already heard that. This is exactly what we're talking about now, right? Optimization methods for a large number of parameters to do this in an efficient way. And there's more than one method because the optimum method to select depends on the nature of the equations, whether they are very nonlinear, whether step changes, how well they're connected or not. There's not one best method. So if the response surface is the objective function as a function of the parameters, right? To parameter 1, parameter 2, and how close we are to the observation. This is called the response surface. If the response surface is smooth, well-behaved, you can use very efficient parameter estimation method. You don't need many simulations. If it's not well-behaved, particularly if it has local minima, it's not well-behaved, then you need more expensive method that need to simulate much more. And if it's these are nonlinear equations, a couple differential equations which are never well behaved, and if you have a threshold like for the water level bank full, your suggestion still less well behaved, so you need more iterations to get the parameters. But of course you need the observations. And I have one example. Can we bring up the other? Can we bring up the other paper I sent you? Did you receive it? The Marlies paper. When you have socio-hydrological models, they are usually more nonlinear than the models you're used to in other fields of water science. So Susanne has been working a lot with groundwater models, I believe. A groundwater model simulates the subsurface flux of the water, how much water flows under the ground in the saturated zone in groundwater, as a function of the water table. So if the water table is steep, there flows a lot of water in the aquifer, right? And this is a linear process. It's a linear model. Linear model is very well behaved. So groundwater models can be calibrated quite easily. Well, if you have data, right? Relative to the data, right? And there are also subtleties with that, because from the groundwater level you don't get the fluxes, just the relative fluxes, and we're interested in the fluxes, so it's not that straightforward. But with socio-hydrological models, they are non-linear, so even less well behaved. And that's why what I recommend is not only to estimate one parameter, but a distribution of the parameters. For each beta, I'm not saying what is the best beta for the data at hand, but what is the beta, the distribution, the likely distribution of the beta parameters. You know what a distribution is, a probability density function. So we have a most likely value, but it could also be this value and this value. And there are methods for doing that in R and in other software. You don't have to invent these methods. The method I've been using in my group is called MCMC, Monte Carlo Markov chain Monte Carlo market. It's a method that does simulations in a very clever way, and then it estimates the distribution of the parameters. And if you bring up the, why is it HU? I sent you the paper, didn't I? Ah, okay. I sent you only, didn't I send you the PDF? Anyway, then if you have the paper, it's very good. There's a WR paper of Malise. She's a socio-hydrology student of mine. And Alberto Viglione from, the second author is Alberto Viglione from Turin in Italy. He's very good in socio-hydrology. So if you're interested in socio-hydrology, this is a very good address in Italy to go to, Alberto. Okay, can you just scroll down and towards the end, we have towards the end of the figure, it's about the flood modeling. Towards the end, so it's one of the last figures. So all these equations. This is a case study in Germany, near Berlin, at the Elbe River. Stop. So this, can you magnify this? So this is a similar model to what we have discussed today. It's about flood damage in the Elbe region. Just the other, not the other figure. This one. Okay. On the top panel shows the discharge, which is an input to this particular model. Some models it's internal, but this is external. And for each year, you have the maximum discharge at the river, the Elbe River in eastern part of Germany, the maximum discharge at this location in Dresden, Saxonia. Dresden, Saxonia. So big bars mean big flood. Okay. So this is the top panel. Then the other panels are already the outputs of the model. The red is simulated by the simulation by the model, and black is the data. The entire thing starts in 1789, right? 1789 and goes until 2020. And the data points we have settlement density. So how many people live in the floodplains? And we have data points, which is the black points here. Not for the entire period, because we just didn't have data all the time. So the density is here 0.15, and then it's 0.25, etc. And the error bars in the black points tell us the uncertainty of the measurements. The black points are the measurements or observations taken from old newspapers or archives, chronicles, because it's a period of almost 250 years. And then we have on the second panel the losses. We have some data in the year 1798, financial losses, and of course we need to account for inflation over this period. And then the more recent ones at the end, 2002 flood and 2013 flood, we have very good data on the losses. And then awareness, this is the second from bottom, the second from bottom panel. We only have data in the past 20 years because our colleagues from Germany, they have made surveys. They have sent out questionnaires to the people in Dresden and asked them, are you aware that there's a flood risk? And they did this a couple of times over a period of 20 years. And these are the black bars. And they have not only asked about awareness, but also of the preparedness. Is there a flood? And do you think there's a flood risk? That's awareness. And did you do something about that? That's preparedness. Did you flood-proof your house, as we saw this morning? No, that's preparedness. Again, the black points, when we don't have data about the past of that. Now, the red lines is the calibration of the model. So you don't see the coefficients, the parameters here, but with the calibrated coefficients, if you run the model, you get these traces. Another point is, we're not only using one set of coefficients, but a distribution of coefficients, which gives us error bars, plus minus 1 the standard deviation, the dashed lines. And because the model is non-linear, the error bars, the uncertainty bounds, are bigger than for hydrological models because of the nonlinearity, right? And for such hydrological models, I can recommend to use this kind of calibration procedure because the software is there. We just need to parameterize this, of course, but it's not very difficult. And the advantage is you get not one parameter set, but a distribution of parameters. Maybe the next figure shows it, maybe distribution of parameters, I'm not sure. Not this one, further down. There was, I think, something that looked like distribution. What is this? Are these the coefficients? Yes, no, this figure. So these are different parameter values and how they are correlated. In a model, ideally you would like to have parameters that are not correlated. If the parameters are correlated, they are difficult to identify. You understand what I mean? No. Some of you do, others don't. Let's consider the following model, just hypothetical. Okay, the model reads y, which is the model output, is alpha, which is the parameter, times x, which is the independent variable, plus beta, coefficient, times x, independent variable. Okay, can you estimate alpha and beta from data of x and y? Can you do this or not? You can? Okay.
How to calibrate alpha and beta?
How to get rid of beta? Yes, very good.
Okay.
The question is how you can estimate beta and alpha independently.
Independently?
I want the value of, I give you data of y and x.
Mm-hmm.
And I would like you to give me values of alpha and beta. Deal?
Yes. Mm.
Mas nesse caso aí, você pode fazer só.
Yeah, I fixed one.
I think there's a comment here.
I think that you can use multiple linear regression.
So, but what is the value if I give you y and x? How can you give me alpha and beta? Or no?
Yes.
No.
No?
No.
Because if you can have.
Oh, yes. So more than one, yes. Yes.
Can you repeat it? Yes? You're just putting it very nicely.
You have different combinations of alpha and beta that gives the same result.
Exactly. You have multiple combinations of alpha and beta that give the same results. This is a trivial case, right? This is very simple and easy. But in the more complex models, you can also get something to this effect, something similar. If alpha and beta are correlated, they are very correlated in the equation down there because they're one-to-one correlation, right? If they're very correlated, there's like these two. Here, these two parameters, I'm not sure what the names are, but these two parameters are quite well correlated, or these two, which is not so good. You want to avoid that, because then you cannot identify them very well. Okay? And the way to do this, one way, for example, here, I would just remove the beta, right? This model does the same thing. It's good enough. We don't need the second term. Reduce the number of parameters. Okay. This is step 6, right? Okay, can we go back? Any questions? Step 6? And then we do step 7. No. Any questions on step 6? Please go ahead. Some consultation going on.
They're discussing about the calibration and all these things.
Okay, I think some consultation is okay.
Can you explain again, please? Just that part when you say, for example, we have to test 10,000 times, for example, or 10 to the 18 times, for example. How do we make it easier?
How to do it?
Yes, how to do it in an easy way.
Easy way.
Yes. Possible way, maybe.
Yeah, possible way. Okay, now I'm plotting the response surface. This is parameter 1, and this is parameter 2. And what I'm plotting here is the sum, z, the objective function, is what variable do we take here? G is the sum over all time steps. E is 1 to n of G simulated minus G observed squared. This is Z. Observation is what we measure. Simulation is what the model gives us. The difference squared, summed over all time steps, is what we call the objective function. Objective function, which in which case we want to minimize, okay? And then I run the model with different parameter combinations, beta 1, beta 2, 100 times with these parameters, 100 times with these parameters, and with all combinations. So I run the model 100 times, 100 times, 100 times with this parameter, 100 times with that parameters, and all combinations, which is 10,000 times I run the model. And each time I evaluate this equation. And in each time independently, I compare the simulations, which are different in each case, with the observations, which are the same in each case. And then I plot it. And I plot a response surface, which can, for example, look like this. And here is the minimum. And these are isolines of the Z. This is Z, right? The isoline, the minimum value is here. So I think the best parameter combination is this parameter value and this parameter value. Okay? And this is also where the term Pareto that Gabi has been mentioning comes in. If you have a strong dependence, right, then you have different values you can combine. Actually, it's not quite true because Pareto is usually for different objective functions. Anyway, let's focus on that. You have one parameter, the other parameters look at the response surface and take the minimum. Now, 10,000, 100 times 100,000 simulations is what I call brute force. You understand? Brute force? Brute force. Not clever, brute force, stupid. And if you have 10 to the 28 simulations with 14 parameters, or 10 to the 30, you cannot do that. No way. Then you need clever methods of finding the optimum, and you start with a starting value. You start here, for example, with this value, and then clever methods find a clever path to the minimum. For example, along the gradients, it's one of the possible methods. Let's say I'm going along the gradient to the minimum. So each time, so I have not 10,000 simulations, only I make a selected number of simulations and follow the path to the minimum. If it's smooth, this is one possible way of finding the optimization, but there are hundreds of other methods depending on what the response surface looks like, the response surface depends on the model structure. This is a fingerprint of this model structure. Each model factor gives us a different fingerprint of the response surface. Okay? Good. Questions?
So can I set my stopping criteria? Of course, then the metric is, should use my error MSE root mean squared error is that right?
Okay, you're using a term I have not mentioned, which is stopping criteria, right? Stopping criteria. Well, it means the following. This optimization is iterative. I do run it once, the model, check the objective function, run it again, again, again. When should I stop? How many times should I run it? Right? It's not 10 to the 30th, so fewer times. And then there's so-called stopping criteria that tell us when it is time to stop, right? And usually not running the computer for 3 hours. It's not a good stopping criteria. But for example, the magnitude of the objective function, or better, how much the objective function improves between the iterations. If you simulate, you always get the same result, then I'm at the minimum, right? So change in the objective function is a typical stopping criteria. A small change. Whatever small is, right? Then people try it out. Okay, how do we go time-wise? 30. Very good. Step 7, or more questions? Step 7. Okay. Would you like to comment on step 7, or should I start? Yeah, fine, fine, fine. No problem. Okay, step 7.
Oh, yeah, sorry, we have 5 more minutes, right? 5? Right. It's until 5:30. Oh, is it? So 5 minutes. But do you want to continue to 6 o'clock?
What about our campuses? Well, tomorrow we have another unit. Agree? Okay, 20 more minutes. So which allows us to finish step 7, and then tomorrow we can do other things. What we do with these models in the context of water management. Okay? I think this makes sense. Step 7. Now what we have at the end of step 6, we have a calibrated model for our data. It's calibrated, and we're happy with the model structure. But we do not have full confidence in the model yet because we tested it for one data set. And people who want to use the model, colleagues or water management, will ask you, why should I trust this model? You've calibrated it to 40 years of some Carlos city data. Why do you think is it applicable in my city? Or why should it be applicable to the future? We discussed it, trust, right? And that's why we have the step 7, to build trust in the validity of the model. This is a good model, okay? This is what the role of step 7. And then what can we do here? Test the model against independent data. So independent data. This is it's called a split sample test. So we have a total sample of data, and we split it in 2 parts. The first part we use for calibrating the model, finding the optimum coefficients, and the second part is used for testing the model, not for estimating the parameters, but we run the model for the second part of the data. And usually, the data are split in time. You have 50 years of data, you split them in 2 periods, 25 years for calibration, 25 years for validation. And then you hope, if the validation works for the second part of the 25 years, it will also work for the next 25 years. You hope. You don't know. But if you do not test, you have less confidence than if you test, and if it works. So if you validate the model against independent data and it does not work, it's possible. What do you do? What do you do? change the topic. Go ahead.
Well, if the model don't respond correctly,
Yes.
when we will need back and restructure my model.
Okay, you've listened. I think this is a very valid statement, nicely worded. If the model does not work well, we need to go back and restructure the model. So maybe there are phenomena in the second period, the validation period, that were not in the calibration period, and we should capture them. Okay, very good. Then we go back and change the model structure, the model parameters perhaps, and then do we validate the model again?
Yes. No,
with what data?
calibration.
We have already used them for calibration. It's a bit of a dilemma, right? So then you don't have used the data, we cannot no longer use them for validation. But this is exactly what you're saying, this is what people usually do, that makes a lot of sense. Okay, very good. Split sample in time, that's a usual thing, but we can also do split sample in space. We develop the model for São Carlos and then test it for a different city. And if it works for a second city, we can say, well, that's pretty universal, so I think it will work for all the 5,500 cities in Brazil. Okay? So space or time. Validation. Well, that's quite general for all kinds of models, not just socio-hydrological models, also in biology, chemistry, all of the models. Okay, then we can test the model against, which is also a kind of split sample test, not only for different time periods, different spaces, places, but also for different variables. So if you can, for example, calibrate the model for G, Q, W, A, but not use D for the calibration, withhold it, hide it, and use D for the testing. For sociological models, we don't usually have enough data for doing that, because if you have D, oh yes, you use it for the calibration. If you have lots of data, you can do that. Then you can do sensitivity analysis, which is always a good thing. There are two kinds of sensitivity analysis. You're nodding, so who has done sensitivity analysis? Yes? You have, okay. You tell us. Two kinds of sensitivity analysis.
I guess one parameter at time.
Yes.
Then you...
What do you do? Just explain the parameter sensitivity. What do you do with the sensitivity analysis and why?
You use some input data for a period, and then you put all the other parameter fixed, and then you choose a specific parameter and vary it in, I don't know, intervals, like changing from minus 90% to 90% the original value. And then every time that you run the model with the perturbed value, you check the result, the variation in the output. And then you fix that parameter that you were varying for the original value, and then start with another parameter. And then and check the same output. And then in the end, you plot it, and then you can see which parameter have more effect in the output variation.
Yes, very good. All right, this is the most important. Yeah, we'll see a plot in a minute. Can you scroll down the other paper, Mari's paper?
Because
yes? There's a.
Because then
no.
You can look for.
Yes, that's the parameter sensitivity of the parameters, right? Good. This is parameter sensitivity, and it tells you how important the parameters are. There are some parameters you're not really happy with because you say, wow, I'm not sure whether the calibration is very good. Also, the uncertainty bounds are wide. But then if they are not very relevant for your output, maybe it doesn't matter too much. Right? This is the motivation.
Yeah, and then you can make your calibration easier, excluding the unsensitivity parameters.
Good. Yes. Then there's a second kind of sensitivity analysis, which is what?
I'm not sure, but maybe combining parameters.
You can not only vary one parameter at a time, but in a combined way, as the previous plot was with these distributions, what this MCMC exactly does. But you can not only look at the sensitivity of the parameters, but also the sensitivity of the input on the model, like rainfall or population density. If you think that's not very reliable, then you say, well, if I change rainfall, how much effect does it have on the sociological model? And it's also something you can always do. Is always simple and provide some insight, but it's not a full validation. Right? The split sample validation is better than the sensitivity analysis, or you can do both, of course. Very good. Thank you very much. So let's see what this is, this diagram. Nice colors. What do they tell us? Bias and uncertainty of the parameters for different combinations of data availability. This tells us when we have the data, because often in socio-hydrological data, the most recent period has the best data, and when we go back in history, data density decreases. And these are the different parameters, I think, and these are different time periods. Okay, I think we don't need to explain this fully. Can we switch back to please, to the table, what is it, 7, step 7? Very good, on the right-hand side, if there's something. Test the component models against different streams of data. For example, when you can just test one of the equations. It's a possibility to remove the number of degrees. If you just test this equation, for example, here, the one with Manning, you can just test the Manning equation against hydrological data without having to bother about the rest. Then at least you know this one works well. This is the first thing. Test component models against different streams of data. If a phenomenon is repeatable in space or time, split sample in space or time, then it's good. If they're not repeatable, full validation is not possible. No full validation is possible. And because information phenomena has been used for the parameter estimation. We have discussed that. Sources of uncertainty may include non-optimum behavior of humans. So people that do not respond like Homo economicus. Okay, that's it. Comments, questions? Maybe we can ask the other campuses whether they have more questions. No, Temus, we don't have it, yes. What? We too, okay. Then no questions. Then we stop for today. We do have a unit tomorrow.
Yes, tomorrow we will have classes from, we made a change on the schedule. We will have from 10:30 to midday.
So tomorrow, not early in the morning, only at 10:30, we have one more unit when we talk about applications of socio-hydrological models for water management. Okay? Thank you. Thank you.